In this video, I will illustrate the use of multiple regression as compared to simple linear regression with a data set that I created so that it's all fake data, and it's called salary data. If you're in my class, you'll find this data set in the Canvas page for this class. If you're not in my class, then these are the data that I created. There are 40 subjects. Half of them are male, half of them are female. And you can replicate this if you want. If you're looking at this from outside of my class, you can pause this and type in the numbers yourself. I do not have the data set available as a download except in the Canvas shell for this class. And you can see that it goes to 37 here. Here are the final 3 people down here. For gender, 0 equals male, 1 equals female. And then we have years. That's years with the company that we're analyzing the data for. And then salary is the annual salary in thousands. Then I've got another variable here that I will use a little later on. You can toggle back and forth between variable view and data view to take a closer look at what's going on. And the only thing that has coding here is the value for gender. So we can take a look at that, and we see that the value for gender is indicated here for 0 equals male and 1 equals female. When you have access to a data set, it's always a good idea to take a look under the hood at the coding of the data and see what sort of information you have there. And in this case, we don't really have much information in the variable view. So let's go back to the text of the example. Both the text and the data will be available for students to download. And as I describe here, I created this example after watching an episode of 60 Minutes on CBS, where they had the CEO of Salesforce, which is a cloud computing company, a major company in the United States, where the CEO, Mark Benioff, requested a full analysis of gender equity and salary. He was convinced, because they have such a fair-minded work atmosphere at that company, he was absolutely convinced that there was no inequity between males and females in terms of the annual salaries that the employees were getting. And he sort of took this on as a challenge to have his HR department analyze, basically doing a deep dive into the data to see if males and females were really equal in their pay structures. Benioff committed to making changes in the pay structure based on the outcome of the analysis by the HR department, so that he committed up front before the numbers were in that if any gender-based inequity was found, that he would rectify it. And so they crunched the numbers, and it was kind of shocking in Benioff's description of it. It was kind of shocking that actually they had pay inequity, gender-based pay inequity, in every division across the entire company. And it's a very large company. So they set about making the changes, and Benioff stated in the interview in 60 Minutes that the first year of changes cost the company about $3 million. So that's quite a substantial amount. And to be clear, what we're talking about here is different rates of pay for the same job depending on whether a person is male or female. So I wanted to create a data set where we can use regression analysis to investigate such an issue. And I wanted to create one where you could see both evidence of sexist pay structure and evidence of lack of sexist pay structure using the same example. So using the variables here, what we might want to do to do an initial analysis is to just look at the descriptive statistics. So let's open your data set. If you have this up, if you're in my class, then you need to have SPSS running, and you can open that up. And take a look at the descriptives. So we go to descriptive stats and go to frequencies, the most basic form of analysis. And so we can look at the salary outcome in the frequency data. So you just, when you first open it, all your variables are going to be on the left. Take salary, put it over here. That's the variable that we want information on. And if we take gender and put it over there too, that might be interesting. Probably not actually. And if you click statistics right here, you'll get this pop-up, and you can ask for a variety of different pieces of information about the descriptive stats of the variable that we're interested in. All of these are available also elsewhere, such as Analyze Descriptives Explorer, which I prefer for this type of analysis, but let's do this one since we have it open. So this is Analyze Descriptives Frequencies. So we click our optional choices here. I like to use mean, median, mode, standard deviation, skew, and kurtosis. Hit continue and then hit OK. And we get an outcome here. Here are the basic descriptive stats for the mean, median, mode for both salary and gender. Gender is split. It's 0.5 because half of the people are male, half of them are female. And the coding of 0 and 1, it's called dummy coding. It just means that we're using arbitrary numbers. If I go back to the data set, I've always, throughout my years of using SPSS, used 0 for males and 1 for females. No particular reason for that other than I know I'm not going to confuse myself by having numbers that are different if I just stick to that basic game plan. Oh, by the way, you can toggle the view so that if we want to see the words here in the variable labels instead of the numbers, we go to View Variable Labels and flip that toggle, and now we can see the words that are here. That's the value label, and now see we're seeing those words in the data view instead of the numbers. I prefer to see the numbers, so I'll flip that back. If we go back to the output, we can see our different things that we asked for: mean, median, and mode, standard deviation, and skew. Most of these things are meaningless in terms of gender, because gender is a dummy coded variable, 0 and 1. Half of the people were 0 and half of the people were 1. So this column of data here, this column of information, really is irrelevant. But the interesting stuff is here for salary, where we can see the mean salary, the median hang on a second. Okay, so what we see are the different measures of central tendency here and variability. Mean, median, and mode are the primary measures of central tendency. And then standard deviation is the primary measure of variability, how spread out the scores are. But we also are interested in the skew and kurtosis. Skew is whether the distribution is tilted on one side or the other side. And we can see that there's not very much skew. The way to judge this is judge the skew against the standard error of skew. And if the skew is 3 times larger than its standard error, then it's probably too much skew. So we can see that the comparison here is that the numbers are very similar. So there's no evidence of high skew. And likewise, kurtosis, which is how tall or flat the distribution is, there's no real evidence of kurtosis. So it looks like a normal distribution, but there are other ways to look at that as well. We can look at the frequency table, and we see the scores on salary. They're fairly spread out. Most people making somewhere between, I don't know, 68,000 and maybe 88,000. Maybe that would be about the quartiles. But we also get a histogram, and so the histogram is very useful here. And we can see that the distribution of salary is fairly normal. There's a big peak over here. A few people who are perhaps fortunate to have received a lot of raises, they're over here. And this figure really doesn't mean anything. It just tells us that half of the people are male, half are female. So there's no real information here that can be used to tell us whether males or females are making more money. This simple way of analyzing the data just isn't up to the task of doing what we want to do. So we go back to our options, descriptives, and we tried, this was the one that we just ran. Let's try this one, descriptives, and we put salary and gender over and see what happens. And you can see some of the same options here. For the standard deviation, mean they don't have the mode here as an option. So we run that and we get this little basic table. And again, it just tells us the basic summary statistics for each of these two variables independently of each other. But what we really want to do is check the salary for males against the salary for females in the hope that that would reveal whether or not there is gender-based pay inequity at this hypothetical company. So this table is really just doing the same thing that we got up here. It's the same set of information. So let's go back to Analyze, Descriptives Explore, and this is what I usually use when I'm analyzing the basic descriptive statistics of a variable. I go to Descriptives Explore. You can see that I already have salary in there. And what are the options? There's really nothing here, just the confidence interval for the mean for that variable. And plots, let's look at the normality plot, histograms. So we'll do that first just for salary by itself. The thing that I like about using Descriptives Explore as the option for looking at the descriptive statistics is you get this nice table that has everything lined up. You get the statistic as well as that number's standard error if there is one. You can see we have a standard error for the mean and a standard error for the skew and kurtosis. It also gives you the minimum, maximum, and the range, and the interquartile range, which is a useful thing to know. And I mentioned before that there are other ways to test the normality of a data set. This one looks normal. The histogram here looks pretty normal. But we can also check it against the test of normality shown in this box, the Kolmogorov-Smirnov test and the Shapiro-Wilk test. Kolmogorov and Smirnov were two Russian statisticians, and Shapiro and Wilk were two English statisticians who came up with these different ways of measuring the same thing simultaneously, and so both of them really get the credit. You don't want these to be significant. If the numbers here go below 0.05, then it means that you have a deviation from significance. We don't want that, so it's a good thing that they're not. We don't want it to be non-normal. We want normality. Okay, and so we don't really need the stem and leaf plot for this. This is another way of looking at the normality. If you have errors that are far away from the line of best fit here, then it would be an indication of lack of normality. And so we don't really need those for this example. All right, so that still doesn't tell us whether males or females are making more. This is aggregate data with all 40 of the subjects, both males and females, but there is a way to get what we want. And so that's where I'm going. You go to Descriptives Explore, just like we did before, but we add gender and put it into the factor list. Now what's going to happen is it's going to give us a different table, one for males and one for females. And this is what we really want. You can see that in this very basic table of the frequencies, the percentage for each group, it's broken them up by male and female. We've got 20 in each group. And here we see that the male mean is 81.35. That's the salary in thousands. So it's 81,350 per year. Whereas for the females, it's 72,350. So the females, on average, are making $9,000 less per year. And that seems to be pretty strong evidence of gender-based pay inequity. You've got people working at the same company, presumably in similar types of positions. We don't have anything set up here to analyze type of position. So we're just treating it as if everybody has basically the same type of position within the company. We're not measuring CEOs or anything like that. So this would be pretty strong evidence, a $9,000 a year deficit in female pay, pretty strong evidence of gender-based pay inequity. We can see that for the normality for both groups is fine, or that there's a little bit of skew, perhaps skew that's causing it to be non-normal for the females. Let's look at the histograms. Here's for the males. You can see that it looks like a pretty normal distribution. There's a bit of a cluster up here at the top end of the pay scale. And for females, we see that there is skew. It's positive skew. It's being pulled in this direction. The direction of skew is where the tail is pointing at. So if we can envision the curve going like that, the tail of the curve is going in the positive side. So it's positively skewed. There are a couple of females who are making what the top males are making, but you see this big empty space here where for the males you have a whole lot of people. And the females are clustered down here, whereas the males have much fewer people at that level of salary. So again, that sort of reinforces the idea that we have gender-based pay inequity. You can see the skew for the female over here. It's not quite as high as we would like to see it in order to declare that it is a highly skewed distribution, but it's about double. The skew is about double the standard error of skew. So it's reason to consider it to be somewhat skewed, although it's not what we would call heavily skewed. Another way to judge this, and if we wanted to know whether this number, the 81,350, was significantly different than the 72,350, if we wanted to see whether this difference is statistically significant, we can set up a t-test. So we go to Analyze. I'm going to do an independent samples t-test on this data set. And we go to Compare Means, Independent Samples T, and we reset that. So what we do in order to run the t-test is we take gender, put that in the grouping variable. That's the independent variable. And it would be nice if SPSS actually called this the independent variable, but they don't. There are lots of things in SPSS where the labeling seems to be different than the way we talk about things. Maybe someday it'll change, who knows. But we need to define the group, see where the question marks are. So we need to go in and tell SPSS what those numbers are. Now if you recall, a few minutes ago I said that I always, when I have gender being coded into the SPSS file, I always set males equal 0 and females equal 1. So to define the groups, we just click the button here for define groups. Group 1 is the males, so we put a 0 there. Group 2 is the females, so we put a 1 there. And we put salary in the test variables. I always look at options. There's really nothing here for the t-test. You automatically get the confidence intervals, but we don't. There's nothing here that we can select, and we don't need Bootstrap for this one. So you run it. That's from the previous analyses. We don't need that part. Here's the t-test, and what we're interested in is over here. Notice that we also have an F-test. That's the Levine's test for equality of variances. This one tests whether the variance of the first group is roughly the same as the variance of the second group. You do not want this to be significant. If this number is significant over here, that means you have to skip down to the row down at the bottom. But fortunately, the Levine's test here is not significant. This number would have to go down to 0.05. Again, if this goes into significance, then you violated the assumption of equality variance for the t-test, and you would use the bottom row. This is an adjusted value. The variances are almost the same here, so you don't see any difference between these two numbers for the t-test. But if we had variances that were substantially different for one group versus the other group, we would see that difference play out here with an adjusted t-test value that could be much different. At any rate, for our purposes, we can just stay over here on the top row. We see that the t-test result is 2.215. We can round that off at the second decimal point to be 2.22. And the p-value is 0.033. Pay attention or remember that p-value because we'll see it again. And that tells us that there is a significant difference. It might be useful to graph it out, to graph this significant difference in a bar graph. That makes it a lot easier to see. So if we go to graphs, I'll show you how to make a bar graph of this difference, the mean difference here of $9,000. We'll be able to see that if we build a bar graph. So I go to legacy dialogues. They're just easier to use than the newer dialogues for making charts and graphs. Legacy dialogues bar, and it's a simple bar chart. You can see that I already have it set up here. Let me reset it so that you can see what I do. I take gender, put that down here. That's the x-axis in my bar chart. That's what's going to be along the x-axis. And then the thing that we're measuring goes up here. And I'm going to click mean because that's the thing I'm interested in doing. That's going to compare the mean of the first group against the mean of the second group. And I'm going to use salary as my variable, my test variable for the bar chart. And click options just to see what's there. I always like to see the error bars in terms of confidence intervals. I never use the standard errors or standard deviations. Some people do. It's kind of confusing in publications. People should be all using the same thing. I use the 95% confidence interval in my bar charts. So I click continue and then hit OK. And now we've got a nice bar chart that shows you the difference between males and females. And these are the confidence intervals around the mean. So the mean here, that's the actual number that you see right here, 81,350. That is right here. And 72,350, that would be right about here. So you can see that there is a pronounced difference, and it's statistically significant. It doesn't look as impressive because the bars here are kind of fat, they're wide, but it's there. You can see it. Yet another way to analyze the association between gender and pay for this company is to run it as a correlation. So you can do that here. Now I don't recommend when you're analyzing data to use every single one of these. Ideally you'd have a pretty good notion of what it is that you want to do before going in. But I'm showing you here that several of the different methods that we have will give you essentially the same answer. So again, so we go to Analyze Correlation. It's a bivariate or two variable correlation. And again, you can see that I have it set up already. Normally it's like this. We take gender and salary. You can highlight both of those at the same time using the control key on your keyboard and move those over. Technically speaking, because gender is a dichotomous variable of 0 and 1, you're not supposed to do a correlation with dichotomous data. Technically speaking, since one of these is interval, that's salary, and one of these is nominal, or I guess you could potentially say ordinal, that's gender, it's really a point by serial correlation. So you can still run it, but just understand that it's not a typical Pearson product moment correlation coefficient. Click options to see what's there. It's not much here that's useful to us, so I don't think we need those. And let's get the correlation. And the correlation is negative 0.338. Again, showing that as you switch from male to female, females are making less salary. It's negative because females have the higher number in the 0 and 1 coding for gender, and you can see that it's repeated down here. Along the diagonal, you always get the correlation of the variable with itself, so this is meaningless. This is always 1. And you get the same correlation repeated twice. Now that 0.033 for the significance, notice that that's the same number here. You get the identical significance value. And in fact, if you transformed the t-test into an r, you would get the same number. You can do that by taking the formula t squared divided by t squared plus df, and then take the square root. That way you can transform a t-test into an r, and if you do that, you'll get the exact same number as you have here. So two different ways of getting the same information. That is to say, there is an association here between gender and pay, and it seems to be the case that it's a negative association, that females are getting less. So again, the question is whether or not this is sufficient evidence of pay inequity at this particular company. Now let's do a little bit more of a detailed analysis. Let's do a regression, and that's the whole point of this example. What do we get when we run it as a regression? So I'll do this as a simple linear regression using gender as my predictor and salary as my outcome. And again, you can see that I already have it set up here. If I reset it, salary goes here and gender here. Let's start first with just this one predictor. I had it also with years, but let's save that for a moment and just look at gender. And in statistics, we don't need the collinearity until we add a second independent variable. So let's just look at the descriptives and the confidence intervals. And in order to check for heteroscedasticity, we should put the predictor in X and the residual in Y. The Z score for the predictor goes in X and the Z score for the residual in Y. This will tell us if there's a violation of heteroscedasticity. Well, the assumption is homoscedasticity. It'll tell us whether or not we violated by having heteroscedasticity. So we run the data, and you can see the correlation pops up again here with a simple linear regression. The model R is always the same as the simple correlation between two variables. And then R squared tells us the proportion of variance that's being explained by the predictor variable. Predictor variable in this case is gender. So one interpretation here would be that gender explains 11.4% of salary, and that's a lot. The ANOVA model here tells us whether or not the regression is significant, and there you see that same p-value once again. It keeps popping up, and again down here. Because these are all different ways of doing the same thing, in essence. The regression model for a single variable will give you the same significance value as the significance attached to the correlation between those two variables. And the t-test down here, it's the same t-test as the independent samples t-test, but this is the t-test of the predictor within the regression model. And you can see that it's significant. There's your unstandardized beta weight, the standardized beta weight. And your normality curve. But here's where you see whether or not you violated the assumption of homoscedasticity. And this plots out the errors in your regression analysis, and the errors are all fairly close to this line. That tells us that there is no evidence of violation of homoscedasticity. If these were really, if some of these, if you had a big dip over here where they all go down, that would be evidence of heteroscedasticity. So what this means basically is that you have similar variability at low values of X as you do at high values of X. And of course there are only two values, male and female. So again, we're getting basically the same information, and it seems to suggest that there's gender-based pay inequity. One other thing to do is to look at the, well, actually the scatter plot won't be very interesting because the X variable, the predictor, is only 2 levels, male and female. So the scatter plot won't be very helpful. So let's leave that off. So that's the one predictor model. Let's try it now with 2 predictors where the second predictor is years. And if we go back to the data, you can see that we have values here for the number of years, and males, some males have few years, some males have lengthy years of service with the company, and same thing for the females. I don't know, it looks more or less the same, but we can take a closer look at that. So what if we do, what if we look at males and females in terms of years? We can do a t-test. Let's see, compare means, independent samples t-test, and I'm just interested to see if there's a pattern here with years. I already have gender as my independent variable for the t-test. I plug in years, and that's going to tell me whether or not males and females have a significant difference in terms of time at the company, and in fact there is. And that's the whole point, that one group has more years than the other. And up here you can see the group statistics for males and females. Males have an average of 12.75 years with the company, whereas females have an average of 8.3 years. Excuse me. So that's a pretty big difference in terms of the years. It's about, what, 4.5 year difference, give or take a little bit, with males having more years with the company. So what we need to do is we need to run the regression analysis again with years in the company expressed as one of the predictors. So we go to Analyze, Linear, the same thing that we had before, but now we can put years in as a second predictor. And by the way, there are different models or different methods of entering the variables, the independent variables. We're going to stick with enter. The enter method is where you put the variables in simultaneously and see how well they perform. Sometimes it's called forced entry, where you're forcing the computer program to enter them in simultaneously. There's also stepwise, where you put the biggest correlating predictor in, see how it relates in a regression analysis to the outcome, remove the variance from the model that's associated with the first variable, and then add the next one, and so on. And you'll get different results depending on which one you use. With this one, we're just using the basic sort of vanilla version using method equals enter. And we run that. And first up here at the top, we can see the correlations. This is like a mini correlation table. So we have the 3 different variables: salary, gender, and years. Salary is the outcome, gender and years are the 2 predictors. And we can see that both of these variables correlate with salary. And one thing that we're interested in is whether gender and years correlate with each other. So you have to cross-index. Let's do gender over here with years. And there is a significant correlation. We can see the significance down here, 0.006. There's a correlation, a negative correlation between gender and years. And because we have that correlated predictor, 2 different correlated predictors, we need to check to see whether we have a condition called multicollinearity. So before we're going down, I'm actually going to analyze it again, checking the boxes for collinearity diagnostics. You don't use this when you do a simple linear regression, but if you have 2 predictors for multiple regression, then you need to use this to check for that violation. If you violated this, then you may need to go back and figure out a way to set it straight. I won't be talking about that here, just how to check it. So we run it again. Okay, so now my collinearity statistics are going to be included in the table. They weren't before. But let's just start from the top. So we have our correlations. We have our correlations up here. The model R, 0.35, 0.935 rather, R squared. So we're explaining 87.5% of the variance on the outcome variable, which is an incredibly high amount. And in real life, we never ever see anything that high. But it's fake data, so it's okay. But that's a lot. I just want you to understand that. And we can see here the model is highly significant. The f-test here just tells us whether or not this model is significant in explaining enough variance of the criterion, the thing that we're predicting, which is salary, in order to justify the analysis, and it's highly significant. Next, we look at the coefficients. This is our regression table, our multiple regression table, and you can see that years is highly significant. Over here is the significance for that predictor, whereas gender is no longer significant. So gender used to be significant at 0.033. Just remember that you need p equals, this is the p-value, p equals 0.05 or less. Gender used to be significant with p equals 0.033, and now it is no longer significant at all, not even close. So what happened was that when we added years into the equation, gender got knocked out of significance. And then over here we have the collinearity statistics, and let me say something about that. Each of these values, the tolerance and the VIF, they're doing basically the same thing, but in slightly different ways. I don't know if there's maybe one can be in violation and the other not. I'm not sure. I presume that's possible, but the numbers are derived from each other in a sense. So they'll often reflect the same reality. At any rate, so tolerance tolerance is considered bad if the value is 0.10 or less. So we have 0.84, that's nice and healthy. That means that the correlated predictors here were not overly correlated. And then the VIF, that stands for variance inflation factor. And here, you don't want it to be greater than 10. This number is derived by 1 divided by the tolerance. So these two are directly related, but they're in different, I guess you can say different scales. And you don't want this number to be greater than 10. So we have not violated the assumption of non-correlated predictors, even though the predictors are moderately correlated with each other. So how do we interpret this? One interpretation is to simply say that years is a much better predictor than gender in terms of predicting the different pay that people get at this company. I like to use a Venn diagram to illustrate this, and so I'll go back to the Word document that I have for this example, where I have text-based description, and I suggest running a few of the analyses that I already did. And so these things here, the correlation, the t-test, and the different things here, these are all things that I already did using SPSS. And here's these are the examples of the output. When you run it on your own, you can check to see that you got the same thing. This is first with just gender, and then so here's just with gender, and then gender and years. And there's the difference in the t-test scores. Notice that I don't have on this printout, I don't have the collinearity statistics. But I'm going to scroll down, and I got this Venn diagram here, and I think this can be useful to illustrate what's going on. Let me enlarge this for you. Hang on. Okay, so I created this Venn diagram just for this example. When you do Venn diagrams to illustrate multiple regression, the thing to understand is that each variable is represented as a circle, and the circle represents all of the variance that's attributable within that circle. If you don't recall variance, the actual computation for variance is the sum of squares, the sum of x minus the mean of x squared, divided by n minus 1. So this is essentially all of the variance associated with salary. This is all of the variance associated with years, and this one is all of the variance associated with gender. And remember, this is a symbolic way of looking at it. I did not use any actual numbers to generate this Venn diagram. It's just a crude approximation. The point, though, is that we see that there's overlap between gender and years, and that the amount of overlap there would be equal to the sorry for coughing, I'm not feeling well. The amount of overlap is determinable by using the correlation R and squaring it. That would be the proportion of overlap. So that we can see that years and gender overlap, and in fact we determined earlier that males have been with the company longer. And then we have this, both of these are the predictors used in the model. We have the association of both of these predictors with the outcome of salary. And I've set it up so that we've got two different shaded regions, the yellow and the blue. What we're looking at is essentially the independent contribution that gender has in terms of predicting salary, and the independent contribution that years have with predicting salary. Now there's some shared variance. This area here is shared between both gender and years, which is to say it's confounded in a sense. It's confounded data. But this is the pure essence of gender giving you a unique amount of predictive ability in terms of determining salary, whereas you can see that years has a much larger one. The shaded regions are the semi-partial correlations. I've described for you the partial correlation. Semi-partial correlation is a little bit different. I'm not going to go into that now. But one thing to know is that the semi-partial correlation is very close to the nature of the standardized beta weights in multiple regression. So if you go back to the regression equation, let's see, where's the regression equation? Let me find that again. So the standardized beta coefficients right here, the 0.037 for gender and 0.95, that's a huge standardized beta coefficient, gigantic for years, and so we see that it doesn't really match the diagram. But this amount is generally the same thing as the beta weight. It's technically speaking, it's a semi-partial correlation. The two things are the same formula. That is to say, the standardized beta weight and the semi-partial correlation are the same formula, except that the formula for the, let's see, the standardized beta is the same as the semi-partial correlation, except that the formula in the let me start over. Sorry, really I'm not feeling too well. The standardized beta weight is exactly the same as the semi-partial correlation, except that in the formula the denominator for the standardized beta weight is square rooted. Thus the semi-partial R and the beta are the same thing. It's just, to put it simply, without actually using the formula, one has the denominator square rooted and the other does not. So it's just a different metric, but it's giving you essentially the same information. So you can think of these as the, in essence, the beta weight, the standardized beta weight. And you can see that this one is much larger than this one. So what happens in multiple regression is that when you put these in simultaneously in the forced enter method, the enter just using this method here for analyze regression, using this method here, I call that forced enter or simultaneous entry. It's going to take whichever one is biggest, and it's going to use that first. Any overlapping variance is going to be taken away from the other. So the largest one gets a little bit of benefit. Actually, that's more so for a stepwise regression, and I'll show you that in a second. But what happens is that something that's significant on its own, such as gender, where gender, if you look at the linear regression of gender, would have all of this overlap with salary. This part now is not used. And that's why the individual contribution of gender gets very, very small. So next, what I wanted to do is show what would happen if we had a clearly biased pay structure in the company. And I did this showing that men got an extra $10,000 a year just for being male, and that's clearly sexist, and nobody would agree with that as being fair. But the first example that I went through for the last half hour did not provide evidence of a sexist pay scale, but I wanted to see what it would look like if we did have evidence of a sexist pay scale when we run the multiple regression. So I'm going to run this again. I'm going to take salary out, and I'm going to use salary male plus 10. This is the version of the data where all of the males got an extra 10,000 just for being male. So remember that zeros are males. This male got his salary went from 92 to 102, 66 to 76, etc. Whereas the females did not have any bump at all. They did not get any increment, any bonus at the end of the year. So this is the male bonus of 10,000. So we're going to run this again with salary plus 10 as the dependent variable and see what happens. So now the model is still significant. The R and the R squared changed a little bit. It's a little bit more significant than the previous model. And down here, this is where the action is. In the regression table, we see that, well, yes, years with the company is significant and is about the same as it was before, slightly smaller. But here's the interesting thing. Gender is significant. In spite of the fact that years with a company is such a pronounced, gigantic predictor of outcome and salary, giving every male 10,000 a year causes the model to retain its significance in terms of gender being a significant predictor of salary. So that's evidence. If you ran this multiple regression here, and if you put in all the different possible confounding variables that you can think of, and after all of that, if gender remains significant, that would be evidence that yes, indeed, you have a gender-based pay inequity within that workplace that needs to be fixed. Now, if you just look at gender by itself and salary, there could be other things that explain it, like how many years they've been with the company. And if you do all of this and it remains significant, then it's evidence that you do need to fix it. So one last thing to show: what would happen if we did the regression using stepwise instead of enter? So notice the numbers here. Actually, I'm going to use, let's go back here, use the, I'll do it both ways. So I'll use just the regular salary, the previous one where gender was not significant, and I'm going to use stepwise. And click OK. And so now what you get for the regression model is only the variable that's significant, that's years with the company. Before it was 15.5, I think, something like that, 15 point something. And now it's a little bit larger because in stepwise regression, what happens is that if a variable is not significant, then it doesn't get entered into the model. And that allows years with a company to use up all of the variance available to it to explain the outcome, and that's why it gets a little bit larger. So there are differences based on which version you use, which version of the entry method. Let's try it with salary plus 10 and keep it with stepwise. And so now you see what happens, and this is a good example when you have two different significant predictors in stepwise prediction, stepwise regression rather. You get a model that changes. You have two different steps here. In step 1, you just take the biggest predictor, put it in, let it have its way, and then you take the second largest significant predictor and put that one in, and you see that it changes from one step to the next. There are important differences between the simultaneous or forced entry method and stepwise regression method. There's some decisions that researchers need to make in terms of which one to use for what purposes. I won't go into that here. I just wanted to point out that you do get different answers depending on which method you use. Okay, so that's all I wanted to talk about today. I hope you found this useful. Thank you.